Okay, so there we go. We're starting. Hi, Alan.
Hi, Alan.
Hi, Alan, and anybody else who might actually be willing to watch this, but it's probably just Alan at this point. That's right. So we have two topics we're going to talk about today, and I gave you guys the handouts already. We're going to do implicit differentiation, and we'll talk about related rates. All right, and now we'll go through our presentation for both of those, and then give you guys a chance to practice those if you guys would like to. We'll go through those. All right, so implicit differentiation, the big thing with this is that this is when X and Y are mixed together. They're going to be on the same side of the equation. We've got X's and Y's, and you got to know all the derivative rules. You have to remember every time you take a derivative of a Y, you also have to do a dy dx or a Y prime or show some way that we're taking the derivative as it relates to X, but that Y's are mixed in there as well. Last week, we were talking about separable variables. This is kind of like the opposite of that. This is where instead of having the derivative already given to us, we are taking the derivative and going from there. So derivative is often given, could be given, and students are required to show that it's correct. The follow-up is the answer questions about the function, such as finding an extreme value, a second derivative test, or where the tangent is horizontal or vertical. So there's lots of different things that might show up in an implicit differentiation question. But the same rules apply. You still have to know about how derivatives can help us to find maxes and mins and slopes. Second derivatives can help us talk about concavity. Just because we're talking about something that has both X and Y in it, the rules don't change. We just have to know exactly what we're going to do. And so a lot of times we'll have to go through and show different things here. So, all right, here's what students should be able to do. Right? Know how to find the first derivative of an implicit relation using the many derivative rules let me know. This was stated in the opening little paragraph here. Sometimes question A is literally just, here's our original problem. Question A is show that dy dx equals this thing. Okay, and the whole point of that, when you do that, I don't think that's on the one that I have for you guys here today, but we've done different ones like that in the past. The whole point of that is that they want to show that, or they want to see that you know how to do implicit differentiation. But they also want to make sure that if you screwed up implicit differentiation in step A, you can still move forward into step B, C, and D, because you need that derivative to move forward. And so instead of question A just being find dy dx, okay, they are expecting you to match up dy dx with something that they already have. Just in case it goes wrong, which hopefully it doesn't, you guys should be able to still move forward there. Know how to find the second derivative, including substituting for the first derivative. And what that means is that while you're taking the second derivative, most likely at some point along the way, dy dx is going to reappear because you're going to have to take another derivative of y. And when dy dx reappears, you have to remember, wait a minute, I've already defined dy dx, or it was defined for me earlier in the problem, and I have to then resubstitute that in. And so you put dy dx into that as well. So your final answer should still just have x's and y's in it. You shouldn't have x's, y's, and dy dx. Know how to evaluate the first and second derivative by substituting both coordinates of a given point. Note, if all that is needed is the numerical value of the derivative, then the substitution is often easier if done before solving for dy dx or d squared y dx squared, the second derivative. And as usual, the arithmetic need not be done. So you might not have to simplify necessarily. If all you're trying to do is show if something is concave up or concave down, you might just have to find is it positive or negative for the second derivative. You might be asked what the second derivative actually is, and at that point, then you have to obviously find the actual numerical value. It all just depends on what they're asking for. Analyze the derivative to determine where the relation has a horizontal tangent, meaning the numerator is 0, or vertical tangents, meaning the denominator is 0, which would make the slope undefined. All right, so a lot of times you end up with fraction situations, and sometimes you have to focus on just the numerator or just the denominator if you're trying to figure out where a horizontal tangent is or where a vertical tangent is. And so at that point, you're just focusing on one versus the other. Okay, don't set both of those equal to 0. That creates a hole, okay, which could be asked, but is unlikely. Normally, you're asked for tangents of either horizontal or vertical nature there. Write and work with lines of tangent to the relation. Obviously, if you can find the slope and you know some points, they can ask you to work with the tangent line and understand where the tangent line is. Again, there might be a follow-up. This came up last week when we were doing a topic, knowing the concavity. If the graph is concave up versus concave down, where's that tangent line going to be in relation to the actual graph? And will it be below the graph or above the graph? Okay, because the tangent line is just an approximation. It's really, really close, okay, but it's not the exact value. So it's just underneath when it's concave up. Is it just over the top when it's concave down? That might be something that you work with as well. And then find extreme values. It may be necessary to show that the point where the derivative is 0 is actually a point on the graph to justify the answer. And that's an important feature. If they ask you about a certain point, not only do you have to find what the slope is or prove that it is a horizontal tangent or a vertical tangent, you have to show that that point actually exists on the original graph. So make sure that you do that as well. Take that point, okay, and plug it back into the original equation to make sure that that point even actually exists. I've seen that on other questions. I don't think it's on the question that you guys have here today, but I've seen that on other questions where they give you a point where the tangent line would have a slope of 0, but that point doesn't even actually show up on the graph. Right? And it feels a little mean that they would do something like that, where they'd say, find this value, but it turns out that that's kind of the whole point of that, is to get you guys to understand and to show that it's not just where the point is equal to 0 or where the slope is equal to 0. That point actually has to exist on the graph itself. So again, it kind of feels a little mean-spirited, but you need to make sure that you guys show that. Okay? Or you might have to show that if you look at the scoring guidelines. I've seen this on other questions, but that point does exist, but you don't get full credit by not showing that that point was on the original graph in the first place. Like, yes, this point is actually a point that exists on the graph. So make sure that you guys do that. If you have questions about that, I can show you guys later on about that. All right? That is implicit differentiation. All right? Any questions on that? No. Okay. I will give you guys the handout for that, or the question for that coming up in a little bit. You guys have a couple of them there. 2004, number 4 from AB. 2016, number 4 for BC. I'm going to give you guys the 2016, number 4. That's a BC version. Obviously, that's a little bit more applicable for you guys. And you can work on that. Or again, the key for that scoring guidelines are on Canvas. You can go on there if you need. Okay. All right. Our other topic for today is related rates. And this is a totally different category of questions. And so just to completely shift gears here, but something that you guys might need to be able to do. The key with related rates is understanding that derivatives are rates. And when more than one variable is changing over time, the relationships among the rates can be found by differentiating with respect to time. That's the big key here, is that time becomes a factor in these as well. Is that not only are we worried about the radius and the height of some object or the length and the width of some object, we also have to bring time into that. So these things are changing over time. And as things change over time, you also have to understand that one thing is going to affect the other thing. And so there's going to be lots of some d something dt in here as we go. And so we'll talk about these. Lots of geometry involved in these as well. Guys, so you're going to have cones in here. You're going to have spheres in here. You're going to have cylinders in here. You're going to have all sorts of different geometric shapes that are changing somehow. It's a snowball that is melting. It is a cylinder that is filling up with water. It is a funnel that is shaped in a certain manner. Okay, that's maybe it's a cone-shaped funnel, and water or sand or something is pouring out of it. Okay, different things like that. So what do you need to be able to do? Well, you need to be able to set up and solve related rate problems. Okay, and obviously the key with this is that you got to start with the geometry. Hopefully, it's either a geometric figure you're familiar with, or they give you the formula for it. And so we'll talk about that as we go. Be familiar with different standard types of related rate situations, but also be able to adapt to different contexts. Okay? If it's not a geometric shape that you're comfortable with, what do we do? And how do we adapt to that? We'll have to figure that out on the fly if you guys get a question like that. Third bullet point, and this is kind of the key with all of these in general, okay? Understanding that we are differentiating with respect to time. We're using dy dt or dh dt or dr dt, whatever it is, and any of these, dt is the key thing here because we are saying how something changes over time. We use all of our differentiation techniques, even if there is no time variable in the given equations. The reason that this kind of fits with what we're doing with implicit differentiation is that here we have to do dy dx when we're taking a derivative of a y. Here with related rates, we have to do a d something dt. So there is a connection between implicit differentiation here and related rates. But in related rates, it's all about time. You have to make sure you can interpret the answer in the context of the problem. Obviously, using units is going to be important, and to go from there. And that's an important feature that you guys have, is that you guys need to make sure that you're using the appropriate units as you go. okay, and that you guys can use different rates. Okay, potentially it's a second derivative, so it's feet per second squared if those feet per second are changing as time goes on. So interpreting your answer and then using appropriate units is so important on these different questions as we go, because all of these are going to have some sort of context behind them. You got to use the appropriate story problem. So again, a lot of these questions, so both of these are questions number 4 that I have examples here. I'm giving you guys question 2019, number 4. And these may or may not have your calculator available to you. And so again, question number 4, neither of these would have a calculator there. Maybe if it's a question 1 or a question 2, you'd have that. I would guess many related grade questions and implicit differentiation questions are probably no calculator ones. Those are ones that you don't really need your calculator. Those questions. Makes sense. Good. You got it, Alan? I hope so. Bye, Alan. Bye, Alan.